Okay, so today we'll go over more theoretical stuff. I mean, in terms of questions, but we just, we're sort of near the end, yeah. So, sadly, I thought this class would go over Galois theory, but apparently not. So, uh, so if you're interested in Galois theory, I think that's 120C, I believe. So that's where you really work with fields, but okay. So let me just say, the plan, I guess, for so let me just say no quizzes this week. The plan is for next discussion is I would just go over Wednesday stuff if there's anything new, and then I will leave rest of time for questions. Yeah. If you have any last minute questions before the final, he will go over, send the solutions to the final review. So if you didn't check already, he sent an email with like the final practice questions. So make sure you do that. Okay. So other than that, any questions before we get started? Okay, so we'll go, I'll define algebraic closure, and then we'll do a lot of theoretical questions since we did a lot of computational stuff last time. So we're gonna let definition. So we're gonna let alpha I be an E. I didn't really define this, but it's sort of assumed, right? So alpha 1 to alpha n. This is smallest extension field. Field of F in E containing the alpha i's, right? So, and one thing to note that I didn't really say is note from theorem that finite extensions are algebraic. Converse is not true, or algebraic. We see if alpha beta is in E, are algebraic. Over E. Then so is this, right? So in a sense that every other new element you get is also algebraic. Yeah, so does everyone see this from the theorem? Or like I'm basically saying like root 2, right? Because right now all we did was join root 2, right? The like x squared minus 2, right? So this is saying like every other element is also algebraic, right? Like 1 and root 2 are in here. So 1 plus root 2 is algebraic. 1 minus root 2 is algebraic. Yeah. So like, because again, right now, a priori, all we did was say we had joined the root of x squared minus 2, right? So you might wonder, what about all the other elements there? Are those algebraic? And, turns out they are. So is this clear from the theorem, or do you want me to explain it more? Okay. So let's continue. So now algebraic closure. So the idea is, we need to, what happens when you just keep adjoining all algebraic elements, right? We get a bigger field. So let E be extension field of F, right? Then this is what we call the algebraic closure of F in E, is the set of alpha in E such that alpha is algebraic. Yeah. So it turns out this is a subfield by what I just wrote in the previous page, right? The sum is algebraic, right? It's closed under addition, closed under multiplication. So you can sort of see that this is a subfield of E, and we call this the algebraic closure of F in E. Yeah. So think of, it's the set of, it's the things in E that are algebraic over F, if you like. So the set of algebraic numbers of all algebraic numbers. So what wasn't algebraic numbers? It's just a special case. So these are elements that are algebraic over Q, right? These form a field, right? And if you think about it, this using this notation, this is Q C bar, yeah, where E is C and F is Q, yeah. So for here, using the notation here, right? Because C is like the biggest field, right? So we sort of see that, it's the stuff in C that are algebraic over Q. So let me just say, most books, they just omit the C, they just write Q bar for the set of all algebraic numbers. So let me be very clear, right? Many students mistake this. So if you took 140, right? I'm saying this thing, right? I guess that's why the book uses the C part. This is the algebraic closure of Q, and this in 140, so this is 120B, right? In math 140, you learn like another like Q bar, right? But this is different. This is like the completion of Q. Yeah. Does everyone like get the difference? Like these two are like completely two different sets, right? So this is the set of all algebraic elements, right? So what did you learn in 140? Like, what is the set? What is the completion of Q? When you complete Q, what do you get? Uh, I'm sort of assuming you took 140, but if you didn't, that's fine. But for those who did anyone take 140 here? Yes, no. So it's sort of, you're sort of like completing with respect to the absolute value, right? So the idea is like let me just quickly say, right, that this is not 140, but the idea is like rational numbers are like dense, right? Like any irrational, you can always like put two rationals between it, to squish it in between, right? So like the idea is, you want to take all limits of Q, right? So given an irrational number R, you could find a sequence of elements in Q, right, that go to R, right? Sequence of rationals, right? Like pi is 3.14, blah blah blah. Well, you could take the sequence 3, 3.1, 3.14, 3.141, right? 3.1415, right? So on and so forth, right? These are all rationals that approximate your irrational. So the idea is in 140, this thing is R. Yeah. This thing is not R. I mean, you already learned that pi was transcendental. Yeah. Dental. So like there's no way these two sets can be equal. Uh, Everyone clear on this? Okay. Moving on. So let's define algebraically closed, right? A field F is algebraically closed if every non-constant polynomial in f of x has a 0 in f. Yeah. So an example of non-algebraically closed is f equals q is not an example. Yeah. Because x squared plus 1 is in q of x, but has no roots and no 0 in q. Yeah. And there's an easier criterion theorem. A field F is algebraic. I'll use ALG for algebraically closed if and only if every non-constant polynomial in f of x factors in f of x into linear factors. Yeah. So this, and you learned in long ago that this is true in C of x, right? So C is algebraically closed. So what's the idea here? So the idea, so this is clearly an algebraic, so this is a theorem, but clearly an algebraically closed field F has no proper algebraic extensions. Yeah. So you can't get a bigger extension because you're algebraically closed, right? You already have all the algebraic elements. So I mean, one way to see this is, right, so let me just give you an example to make this clear, right? Take the element I, right? So what is irreducible, the irreducible polynomial of I over Q? What is this? Can anyone tell me? X squared plus 1, yeah? So you see when I quotient out, right? So you see that this is not linear, it's quadratic. So you see here, right? When I quotient out, I get a bigger field. I get, Q of I. It's isomorphic to Q of I, right? So, but let's take C. What you're gonna notice is if I take C, I don't get anything new, right? So if I take, what is irreducible polynomial of I over C? What is that? X minus I. Yeah, it's linear. Yeah, linear. So, right? So when I quotient out, what do I get? This is just C adjoint I, but this is just C, right? Because, I mean, no point in adjoining I. like I is already in C, right? So if you join I, that does nothing, right? So you see, you don't get anything bigger, right? C is like the biggest thing, right? Anything bigger, it's transcendental in a way. So like that's what we mean by like algebraically closed. That's why you don't really learn about any bigger thing other than C, right? In your regular calculus class. It's because that is pretty much the biggest thing in terms of algebraic extensions. Uh, everyone clear on this? Yes? No? Okay. So let's move on. I'm not gonna prove this, but I might go over this next time. I don't think it's that important, but do all fields have an algebraic closure, right? So closure. So basically, right? Like, can I just say take Q adjoin all algebraic elements? That's a field. And the answer is yes. And the notation is we put a bar. Uh, I don't know why I wrote bar like that. Put a bar as notation, yeah? So kind of like how Q goes to Q bar, right? So like the algebraic closure of F3, the field of three elements, if you like, this is Z mod 3Z. We write F3 bar for like algebraic closure. So the proof of this uses Zorn's lemma. Let me just say Zorn's lemma. That will take a long time to go over. And I mean, and you really only have like one question on Zorn's lemma on your homework anyway. So if needed, I will go over that next time. Yeah, it's about like ordered pairs and cosets and like maximal things. But for now, just know that given a field, I can always there exists a bigger field that has all the algebraic elements. Everyone clear so far? Yeah. Okay, so let's do some of your homework questions and some non-homework questions. Yeah. So this is more theoretical now. Yeah, we did a lot of computational last time. So Q, true or false? Q is its own algebraic closure in R. Yeah, that is Q is algebraically closed in R. In other words, is this true? The question is this: is this, which is the set of alpha and R, such that alpha is algebraic over Q? Is this equal to Q? Is the question. Yeah, because the algebraic closure in R is by definition this thing, right? False. Yeah. Can you give me an element in R, not Q, that is algebraic over Q? Anyone will do. Pi is not. Pi is transcendental. Uh, do not pi and the number e, the probably like the two famous numbers in math 2a 2b, those are transcendental. Yeah, you're not gonna find a polynomial that has pi and e as a root that in Q of x. But yeah, like root 2, right? There's a lot like root 3, root 2, anything really, right? So like example root 2. Yeah. Okay, so this is not in the the actual book, but let's make it harder. Um about this? Is this equal? I mean, obviously, from here, it's false, right? But also from what I said, is it equal to R? This is also false, right? Because pi is transcendental. Yeah, there are stuff in R that are not algebraic, right? So you see like Q bar, like this thing is like in between Q and R. Yeah. Okay, but next question. What about this? Are these equal? Okay. So for sure, like, by definition, these are, Q bar R. These are elements in R, right? So these are elements in R, these are elements in C. So can you give me a complex number? So basically, if they were equal, then that would mean the only elements that are the only elements in C that are algebraic over Q are elements in R, right? And so if you say this is false, then you would have to give me an element in C, strictly C, not something that is real, that is not real, that's complex, that is algebraic over Q. So can you give me an element? Yeah, I, good. Yeah. So certainly I is in here, but I is not in here, right? Because I is not real. So yeah, so this is false. Yeah. Is everyone clear on this? Okay. So let's move on. True, false. One more. If E is algebraically closed extension field of F, E is an algebraic extension of F. This should be immediate, right? So if can you give me an example of a field that is algebraically closed? What's the first one that pops up in your head? That I just mentioned. Yeah, C, right? C algebraically closed extension of Q, right? So is it true that C is, and is it true that C is an algebraic extension though? Yes or no? Yeah, it contains pi. Yeah. So yeah, so this is false. Yeah. All right, good, good. So okay, well, okay, true, false, I feel that those, like, even on the final, you have like a 50-50, right? So let's do actual proof questions. So more questions, theoretical. Theoretical. Show if E is finite extension of a field F and EF is prime number then E is a simple extension of F. So if you recall, what does simple extension mean? I.e., E is F of alpha for every alpha in E, not in F. Yeah. So, this might be something, you're going to see a lot of theoretical stuff on your finals. So let's think of how to do this. Yeah. So what's the first step? Or at least, what do you think? You don't have to be right. Just, Um, So what is this question asking, right? It's asking, right? Like basically it's asking, can I have a field between E and F, right? Because certainly if I let alpha be in E, then do you agree that this is true? Yeah. The field F of alpha is a subfield of E, right? It's certainly smaller than E. Yeah, pretty much. That's the idea, right? So how do you argue this? So the first thing is let alpha be an E, then certainly alpha is algebraic. Yeah, algebraic as E is finite extension, right? You had the theorem that finite extensions are algebraic. So alpha is algebraic. So this thing is some number K, right? Now it sorry, take alpha and E without F. Yeah. So take an element in E that's not in F. So first thing is, do you agree that because of this, K is bigger than 1? Yeah. Because if K is equal to 1, then F of alpha equals F. But we assumed alpha was an element in E that's not in F. Yeah, so that's a contradiction if K is 1. So do you all agree that K is bigger than 1? Okay, so there's only like one more step. What's the last step? So what must this be? Use the fact this is prime. So what must this what must this number be? So we're almost there. It's like one more line. So yeah. So it's Tower law, right? It's f of alpha to f equals e to f. This is prime. Yeah. And this thing is k and it's bigger than 1. So if this is also bigger than 1, we have a contradiction, right? Because a prime cannot factor into two things that's bigger than 1. Agree? So it must be that this is actually equal to 1. But if they're equal, then by definition, these fields are equal. And so we are done. So it's a simple extension. Everyone clear? Always use tower law. Yeah. Like tower law is like the strongest things you can use. It's like very powerful. So can I move on? Everyone good? Yeah. So 30. Let's do 29 first. So 30 is your homework question. So I'll do one of the homework questions for you. So, but let's do 29 first. Let E be finite extension field of F. Let alpha and E be algebraic of odd degree over F. Show, whoa. I copied the wrong question. Okay, sorry, that's problem 30. And let P of X and F of X be irreducible over F and have degree that is not a divisor of E of F. Show P of X has no zeros in E. Yeah. So any ideas? How about, okay, suppose P has a zero, then what? So suppose P of X has a zero in E. So let's say, P of alpha equals zero for alpha and E. Then what? What is this then? What? No. Wait, what do you mean by linear factor? Oh, yeah. So yes, it's expressed as a linear factor in E of X, but they tell us, it's an element in F of X. So can you tell me what F of X quotient P of X is? So let's go numeric example. Yeah. No, it's a field. I'm asking you what is the notation for it? Like how about this? F is Q. Let's take E to be, E to has root 2, right? Then in this case, P of X is X squared minus 2. So I'm asking what is the notation here? Like, what do we call this field? Like, yeah, F of alpha, right? This is Q of root 2, right? So if they didn't tell me it was irreducible, I would have to write, instead of P of X, I would have to write irreducible irreducible alpha F, right? But they tell us P of X is irreducible and it has a root. X squared minus 2. X squared minus 2 does not have multiple roots, right? The roots are negative root 2 and root 2. Yeah. So because they tell me it's irreducible, I know that these two are equal. Yeah. P of x is the irreducible polynomial for alpha. So they give it to us that it's irreducible. So from here, this is f of alpha. Yeah. Everyone agree so far. Everyone agree. So again, we have something like this. Now, my first question is, what is the degree here? What's the degree of f of alpha over f? Again, go back to root 2 example. What was the degree there? It's the degree of p of x, right? Right, kind of like q adjoint root 2, the degree of the extension is degree of x squared minus 2, which is 2. Yeah. So now we're almost done. What's the contradiction? Yeah, again, Tower law. So e to f of alpha to f equals e to f. This is degree of p of x. So in other words, degree from what we wrote, degree of p of x divides this thing. And that contradicts this part. Yeah. So by contradiction, it has no zeros. Everyone clear? The solution is very simple. If you like, maybe think through like some concrete examples like root 2 to like help you out. Okay. Does everyone understand the solution at least? It's not, not that bad. Like it might look, easy when I do it, but like, I did, if you think about it, I didn't really give you the answer. I just asked you the tons of questions and eventually you all got it. So, but that's sort of the way you should think of how to do these questions. Yeah. So let's do your homework question. Let E be extension field of F. Let alpha in E be algebraic of odd degree over F. Show alpha squared is algebraic of odd degree over F. And f of alpha is equal to f of alpha squared. So let's do the easy part. Why is alpha squared algebraic? Forget these odd degree part. Like, why is alpha squared algebraic? Yeah, it's the product of two algebraic numbers, right? If you remember, I wrote here, right? If you have two alpha beta are algebraic over, this should be like over f, but sorry, over like the over the small field. then these are all so in other words, I'm taking beta to be equal to alpha here, and I'm multiplying, right? So alpha times alpha is alpha squared. So alpha squared is certainly algebraic if alpha is algebraic. Yeah. So the fact that it's algebraic is clear. Now, in the end, we want to show they're equal, right? But let me ask, which field is bigger? Is this one? Is the left-hand side bigger or the right-hand side bigger? Yeah, I mean, the left side is a field that has alpha, right? So if you have alpha, then you must have alpha squared, right? It's the because you just multiply by alpha by itself, right? It's not clear that if you have alpha squared, then you must have alpha, right? So is everyone clear that so we have that this is true, right? Everyone agree? So does everyone see why we're done with the first part? Why is alpha squared of odd degree? So it tells me alpha is algebraic of odd degree over f. So this whole thing is odd. Yeah. So why does that, this is just, odd even argument. Why does this have to be odd? Yeah, right? If this was even, then it would divide an odd number, right? So we see that this must be odd. Yeah. So we done the first part. Yeah. So now we know this is odd. Everyone agree? Or everyone follow so far? So now we need to show the two fields are equal. In other words, I need to show this thing is one. Yeah. Now, give me a polynomial. What is min, give me a polynomial. No, whoa, I'm bad at spelling polynomial. In f alpha squared of x that has alpha as a root. I'm telling you it's degree 2. What is it? So if you don't like this, how about this? F of pi and yeah, this will work. F of pi squared. So give me a polynomial in f of pi squared of x that has pi as a root. Maybe the alpha is scaring you. So it's quadratic. Yeah, x squared minus pi squared, right? This has pi as a root, and this polynomial is in here, right? Because pi squared is an element of f of pi squared, right? And certainly 1 is an element of f of pi squared. Does everyone get it? So what is my polynomial here? Yeah, it's this, right? This thing has alpha as a, it's this thing, right? I'm just rewriting the top. This has alpha as a root. and it's a polynomial in here, right? So I know that this thing is at most 2 because I just found a like maybe that this is, maybe this is not maybe this is not irreducible, it's reducible, in which case is 1, but I know it's 1 or 2, right? So this is 1 or 2. Now we're almost done. Well, again, why can this not be 2? Yeah, the same argument, right? Is odd, so it can't be this, so it must be 1, and we're done. So they're equal. Everyone follow? All of this is just Tower law. I'm just making use of Tower law and field extensions. So, but this is normally how, all field questions go. You consider the element, do some Tower law argument, and then done. Everyone clear? So let's just finish up with an algebraically closed argument. Yeah. So 35. Show no finite field of odd characteristic. It's true for even, but the proof is harder. So I guess that's why the book doesn't ask you. But is algebraically closed. So do you remember your homework where it asks you to prove that not every element in your finite field is a square? So if you remember, we define a map from F, so let F be finite field of odd characteristic. So you had a homework where you had to show that not every element is a square, right? So define the map X goes to X squared. Then what is kernel of phi, right? The kernel is the stuff that goes to the identity, right? In which case is 1. So these are stuff such that X squared is 1. But we know the solution to this, right? It's 1 and -1, right? The kernel phi has 2 elements. So by first isomorphism theorem, or I guess the book calls it fundamental homomorphism theorem, this thing is true, right? And since this thing has order 2, this thing has order half the group, right? In a sense, it's like almost half. So basically, the idea is in a finite field, not every element is a square. Do you all remember this on your homework? I think it was on your homework. Right, because again, image phi is exactly the stuff that are squares, right? And to show that not everything is a square, well, you just need to show this doesn't have order f cross, yeah, and it doesn't have, it has order f cross divided by 2. So the reason we need odd here is because if it was even, it's possible 1 is -1, right? In which case this thing is just order 1. So the fact that not everything is a square is true and odd characteristic. Like, right, because in Z mod 2Z, 1 and -1 are the same elements. So, but in which case, right, in this case, in a finite field, not every element is a square, then we're not algebraically closed because take alpha not a square has no root. because if you had a root, has no root in F. Yeah. If you had a root, then alpha would have been a square, right? By definition, if you are a root, then that would mean alpha is a square. And that's precisely the definition of algebraically closed, right? We are algebraically closed if and only if every polynomial, every non-constant polynomial has a zero, right? And we just found a polynomial with no zero. So it can't be. So you see that if I give you a finite field like Z mod 3Z, some books write it like F3, the field of three elements. This thing's infinite. Yeah. Because from this question basically shows this, right? So you can't be finite and algebraically closed. So the algebraic closure of F3 is infinite. Okay, everyone good? So I'll probably go over maybe Zorn's lemma and whatever he goes over Wednesday, and then I'll leave the rest of this Thursday section for questions. Oh, right, and one more thing. My office hours this week is today, 2 to 4. Yeah, something came up, so I can't do Thursday. But yeah, and make sure to do your TA evals if possible. So do TA evals. Okay. Yeah. Okay. I'll see you all Thursday then.